Tornadoes that form after dark are 2.5 times more likely to kill you than tornadoes that form during the day. That is not an opinion, that is the data. And tonight, a line of thunderstorms is forecast to push through the Chicago metropolitan area after midnight, with embedded tornadoes wrapped in rain that no one on the ground will be able to see. That is happening tonight. But it is only one piece of a severe weather outbreak that has already produced confirmed tornadoes in Iowa, 75-mile-per-hour winds in Cleveland, a flash flood emergency in New York, an ice storm in Wisconsin, and blizzards in the Dakotas, all from the same system, all at the same time, and tomorrow may be worse. The tornado threat unfolding across America right now is unlike anything we have seen this year, and by the end of this video you will understand exactly why, down to the physics that makes it possible. If this has you hooked, subscribe to the Skylab because the severe weather season is accelerating and we are tracking it in real time. Drop a comment telling me where you're watching from, and if you're in the path of this outbreak right now, let us know what you're seeing on the ground. Now, let us get into it. Part 1. It already started. The number you're about to hear is the thing that wakes up meteorologists at 3 in the morning and keeps them watching radar until long past midnight. It is the number that causes them to send messages to colleagues and to refresh forecast models obsessively. Right now, as you're watching this, there are 436 active weather alerts across the United States. 436. That is not a typo. That is not a dramatic flourish meant to grab attention. That is the actual count as of early April 3rd, confirmed by the National Weather Service. That number includes tornado watches, winter storm warnings, ice storm warnings, red flag warnings, flash flood warnings, gale warnings, high wind warnings, and everything in between. All of them at the same time, across the same country, on the same day, the same system. This is not one disaster. This is all of them at once, stacked on top of each other, each one demanding its own warnings because people's lives depend on understanding which threat applies where they are standing and what they should do. Knowing whether to go to the basement because a tornado is coming, or whether to stay indoors because an ice storm is hitting. Knowing whether to evacuate because of flood risk or stay in place because of blizzard conditions. The warnings are different, the responses are different, but they are all active at the same time, and the system producing all of this is not done. It is not even close to done. It started on April 2nd, and it is building toward something worse. It is building toward Friday. It is building toward a potential escalation that meteorologists are still calculating and processing. But before we talk about what is coming, you need to understand what already happened, because the outbreak people are forecasting for tonight and tomorrow is not some future threat hanging somewhere in the atmosphere. It already started, and it started violently, with debris raining from the sky in Iowa and destruction spreading east toward the Great Lakes. On April 2nd, a confirmed tornado tracked through Washington and Johnson counties in southeastern Iowa near the town of Kalona. This was not a weak rotation that barely touched down. This was not a marginal event. This was a storm with a clear mission, a rotating column of air producing significant damage across the landscape. When a tornado reaches the ground and begins to tear apart a structure, when it rips the wood from a frame house or tears bark off a tree, when it pulls siding from walls and breaks windows and lifts roofs, it takes those pieces and hurls them skyward. You get wood fragments, splinters of metal siding, insulation from walls, chunks of concrete, shingles, insulation. Everything that made up the structure becomes airborne. The tornado becomes a projectile launcher. All of that debris gets lofted into the atmosphere and shows up on radar in a way that nothing else does. Meteorologists call it a debris ball, and it is one of the most important signatures in severe weather forecasting because it confirms that a tornado is on the ground doing damage. On radar, normal rain shows up as a smooth, uniform signal because raindrops are all roughly the same shape. They are spheres or slightly oblong spheres. The radar signal is homogeneous. The reflectivity is uniform. But debris is chaos. Pieces of wood are not the same shape as pieces of metal, which are not the same shape as soil particles, which are not the same shape as pieces of insulation. The radar sees that chaos and produces a signature on the correlation coefficient product. And the chaos from the Kalona tornado was absolutely unmistakable. It was there for everyone to see. It was there on the radar loops. Meteorologists monitoring the storms in real time saw the signature and knew immediately that the tornado was on the ground doing real, significant damage. Multiple tornado warnings were issued for the Cedar Rapids and Iowa City metropolitan areas, covering some of the most populated regions in the state. Warnings were issued because the Hook echo tracked dangerously close to neighborhoods and universities and hospitals. The threat was real. The warnings were warranted. The threat was active and producing damage. And then the storm changed. What happened next is the kind of thing that keeps changing the forecast even as storms develop in real time. The tornado that produced that debris ball was not acting in isolation. It evolved. What started as discrete supercells, individual rotating thunderstorms, each one a self-contained engine of destruction with its own spin and its own trajectory and its own damage potential, began to merge together. They linked up, they consolidated, they organized into what meteorologists call a mesoscale convective system, an MCS. That is the technical term for the phenomenon, but here is what it actually means in practical language. Imagine an individual supercell as a single weapon of destruction. Powerful, focused, devastating in its own right. Now, imagine dozens of those individual weapons linking their forces together into a unified force pushing forward as a single massive front. That is what happened. A towering shelf cloud, a visual manifestation of the gust front marking the boundary between the cold outflow from the storm and the warm air ahead of it, pushed across Illinois heading straight for Chicago and Indianapolis with the momentum of a slow-moving collision. That transition from individual rotating supercells to a unified squall line is a pattern you're going to want to remember, because it is central to understanding exactly why tonight is so dangerous. The structure of the storm system changes the way the tornado threat evolves, and we will come back to that critical point in a moment because it matters to the forecast. As the system continued moving east and growing in scale, it transformed into something different. It evolved. It became a devastating wind producer. The system itself was still powerful enough to cause major damage, but now the damage was coming from straight-line winds instead of rotation. The gust front pushing ahead of the system was like a giant wedge of air being forced downward and spreading outward in all directions. And when that cold air hit the warm air ahead of it, when that density boundary collided with the warm sector, the collision produced winds that were measured and confirmed. The velocity shear at the gust front created instability that was captured and concentrated. And here is something that does not happen very often, something that made meteorologists sit up and take notice and send alerts to each other. A tornado warning was issued for the Cleveland, Ohio metropolitan area. Not for a classic tornado with a rotating updraft and a visible funnel cone descending from the cloud base, the kind of tornado that chasers see and report visually. For something called a mesovortex, a small, intense rotation embedded within the leading edge of a squall line like a tiny drill bit within a much larger spinning apparatus. Think of it as a spin-up that forms along the gust front, the boundary where the storm's cold outflow crashes into the warm air ahead of it. The temperature contrast along that boundary can trigger rotation even in a line of storms that is not a supercell. The mesovortex tracked through the Cleveland metro on radar, becoming visible as a rotational couplet on the velocity product, the rotation signature that indicates potential for tornado force winds. And a measured wind gust of 75 miles per hour was recorded at Cleveland Edgewater, right on the shores of Lake Erie where the city meets the water. 75. That is not wind that you can walk through easily. That is wind that pushes you. Trees came down across the city, power lines snapped and sagged and fell. Transformers exploded as the electrical infrastructure overloaded or as debris hit them. Over 150,000 customers lost power across Ohio and Indiana during the peak of the event, leaving neighborhoods dark in the middle of a spring afternoon and disrupting the lives of millions of people. Dark at 3 in the afternoon, power out, food in refrigerators at risk, traffic lights not working, emergency generators at hospitals coming online. That is the kind of impact from a single mesovortex in a squall line. Meanwhile, 700 miles to the northeast, a completely different kind of catastrophe was unfolding from the exact same atmospheric system. A flash flood emergency was declared for portions of Tompkins and Schuyler counties in New York, centered on the city of Ithaca. A flash flood emergency is the highest level of flood warning the National Weather Service issues. When they issue one of these, they are not using measured language. It means there is an imminent threat to human life. Imminent, not in the future. Now. It is not a suggestion to be cautious or to prepare. It is not a warning to consider preparing. It is a declaration of danger. It is an alert that people need to be getting to higher ground right now. Reports coming in from Ithaca describe something almost surreal for a spring day in April. 4 feet of water on city streets. Imagine walking out your front door and seeing water halfway up the average car's side windows. Imagine driving through the city and seeing water that deep. Imagine being in a vehicle and the water rising around you. Multiple bridges washed out. The force of moving water simply overwhelming the structural integrity of infrastructure that was designed for normal circumstances, designed for normal spring runoff, not for this. The water was too powerful. The force was too great. Emergency scanners lit up with frantic calls for water rescues, people trapped in vehicles in the rising current, attempting to cross roads they thought they knew and that they had used many times before. The Cayuga Lake at Ithaca hit minor flood stage and was climbing steadily, the outlet insufficient to handle the volume of water pouring in from above. Separately, on the other side of the continent, 5 to 7 inches of rain hammered Livingston and Tangipahoa parishes in Louisiana in a matter of hours, triggering life-threatening flash flooding there too. 5 to 7 inches in hours is an enormous amount of rain. That is the kind of rainfall that swamps drainage systems. That is the kind of rainfall that floods highways and traps vehicles. The same system, different timing, different location, same result. Water was becoming a weapon. Water was becoming a hazard. And while all of that devastation was happening in the warm sector, the part of the system where warm moist air fueled the storms and created the instability and drove the convection, on the cold side of this entire apparatus, an entirely different catastrophe was developing. A crippling late-season ice storm, the kind of event that seems out of place in early April, slammed into Wisconsin and Michigan. 1/4 to half an inch of ice accumulated on power lines, tree branches and roads across central Wisconsin and the upper peninsula of Michigan. A glaze of ice that does not sound like much until you understand the weight and the stress it places on infrastructure. Ice is heavy. A ½ inch of ice coating a power line or a tree branch adds hundreds of pounds of weight to something never designed to hold it. Power lines sagged under the weight. Transformers blew. The grid was failing under the load. Ice storm warnings were active for Green Bay and Warsaw, Wisconsin. Cities preparing for the kind of icing event that might occur in January or February in the depths of winter, not in the first week of April. The ice was accumulating fast enough that crews could not keep up with clearing roads, and that power companies could not keep up with repairs. Now think about that for a moment, because this is the part that makes meteorologists grasp for words. Ice storm warnings and severe thunderstorm warnings were active in the same state of Wisconsin on the same day. The same state. The same state on the same day was expecting both ice and hail. Green Bay was bracing for ice while the southern part of the state was under threat of damaging hail. Going from ice storm conditions to hailstorms in one state in 24 hours is not a normal forecast. That is not the kind of transition spring typically brings. That is the kind of temperature gradient produced when 2 completely different air masses slam into each other, when the contrast between them is so extreme that the atmosphere is forced to choose between winter and summer, and that gradient is the underlying engine driving everything happening on this day, including the tornadoes that are about to form. North of the ice, it got even colder. Parts of Minnesota and North Dakota were experiencing snowfall rates of 1 to 2 inches per hour, which sounds almost cartoonish until you realize what that means for visibility. Whiteout conditions, people standing outside unable to see the hood of their own cars, unable to see the road, interstate closures. Traffic backed up for miles as drivers realized they could not proceed safely. Blizzard conditions, genuine blizzard conditions with wind gusts topping 35 miles per hour, were unfolding in the same country that was producing tornadoes 600 miles to the south. The same system was producing both extremes simultaneously, in different parts of the same country, on the same April day. The temperature swing across the system was measured in the hundreds of miles, the latitudinal extent of the dangerous weather spanning from the Mexican border to the Great Lakes. If this is sounding familiar, it is because it should be. 2 days ago, in video 38, we told you that forecasters were alarmed about what was coming over the next 5 days. That was the warning video, the heads up that something significant was on the way. Now we are in it. And it is delivering everything that was forecast and more. But there is something deeper here that bears directly on understanding what we are looking at. We have seen this exact pattern before. Not years ago, not even months ago, weeks ago. In mid-March, Video 21 covered a compound event, a multi-category simultaneous disaster with all of these same elements. Simultaneous blizzards, tornadoes, heat waves, and wildfire conditions, all from one atmospheric system. That video hit 160,000 views, and the reason it resonated so strongly was not the weather itself. It was the recognition that hit people when they watched it. People saw it and knew something was off. This was not normal. This was not the kind of pattern that springs used to bring. And now it is happening again. Same mechanism, same simultaneity, same multi-category nature, just a different week, just a few weeks later. The pattern is repeating faster than it used to. That was day 1 of this outbreak, April 2nd. And here is the part that should get your full attention and keep it there. What is happening today, April 3rd, and especially what is forecast for tomorrow, April 4th and 5th, may be significantly worse than what already occurred. The system is intensifying, the atmospheric ingredients are coming into better alignment, the models are trending toward higher impacts. But before we get to that forecast, before we talk about what Friday might bring, you need to understand exactly how a tornado is born, because that is the only way to appreciate why this particular setup has meteorologists across the country watching the same patch of sky with genuine concern. Understanding the mechanism is understanding the danger. Part 2, right now, the April 3rd threat. As of this recording, the Storm Prediction Centre, the organisation within the National Weather Service charged with identifying severe weather threats before they happen and issuing risk assessments to the public, has issued an enhanced risk for severe weather on April 3rd. Enhanced risk is level 3 out of 5 on the severe weather risk scale. It covers Chicago, Milwaukee and the Davenport Quad Cities area, a region that encompasses millions of people and includes some of the most densely populated parts of the Midwest. A slight risk, level 2, extends from the Michigan thumb down to St. Louis, spreading that threat across a much larger footprint. A marginal risk, level 1, reaches as far south as Memphis and Little Rock. Tens of millions of people are under some level of severe weather threat right now, and that threat is not theoretical. It is not a forecast for next week. It is happening today. It is active. It is unfolding. The atmospheric setup driving this is textbook meteorology in the worst sense of the phrase. Textbook means we have seen this configuration before. We know what it produces. We know the outcomes that follow from this pattern. A vigorous, negatively tilted upper-level trough is lifting northeast across the upper Great Lakes. If you are not a meteorologist, if that phrase means nothing to you, here is what it actually means translated into plain English. A massive wave in the jet stream, the river of fast-moving air at the top of the atmosphere where the winds exceed 100 miles per hour, is amplifying in height and diving southeast toward the Great Lakes. The trough is deepening. The system is strengthening. As it does, it is pulling everything in the atmosphere with it, wringing energy out of the system like twisting a wet towel until every drop of moisture falls out. It is extracting every available bit of instability. The upper-level winds are speeding up as the system intensifies. The air is sinking in some areas and rising in others, depending on where you are relative to the trough axis. The whole structure is becoming more pronounced and more intense. A surface low-pressure system is tracking through the region with all the infrastructure that comes with it, all the boundaries and the fronts and the wind convergence. A cold front is crashing in from the west, the boundary between the warm air currently in place and the cold air mass behind it. The cold air is coming. The contrast is building. And just ahead of that cold front, a dry line is developing, a boundary between hot, dry air from the west that has crossed the Rockies and warm, moist air from the Gulf that is surging north. Two separate boundaries, two separate triggers, two different release mechanisms for the instability. That gives the atmosphere two distinct opportunities to set off the instability that has been building all day, two chances to launch storms into the sky. And that means two rounds of storms in sequence, each one with different characteristics, each one with its own threat profile. The first round is expected to form along the dry line in the afternoon. This is where hot, dry air from the elevated terrain of the Rockies smashes into the warm, moist air flowing north from the Gulf of Mexico. The density contrast along that boundary is extreme. Hot air is less dense than cool air, and when the density difference is sharp, it forces the warm air upward violently. Supercells are expected to form along this boundary in the late afternoon, bringing damaging winds and hail into the system. But the second round, the one that comes later, along the cold front itself, is the one that has forecasters most concerned. That is where the highest tornado risk lives. That is where the nighttime QLCS is expected to push through. That is where people are asleep. Storm relative helicity values are extremely high across southeastern Iowa and northeastern Missouri right now, values that have meteorologists paying close attention to every update. Storm relative helicity, abbreviated SRH, is one of the most important numbers in severe weather forecasting, arguably the single number that best predicts whether a thunderstorm will rotate and produce a tornado. It measures the amount of rotational energy available in the atmosphere for thunderstorms to tap into. Think of it this way. The wind shear, the change in wind with altitude, creates a spinning motion in the air, a horizontal rotation that is always present when winds change direction. When a thunderstorm's updraft tilts that horizontal spinning into the vertical, the storm begins to rotate. When SRH is high, there is a lot of that horizontal spinning available. The air is primed to rotate, the conditions are loaded for rotation, and right now, across the enhanced risk area, SRH is loaded with rotational energy. The forecast timeline for today looks like this. If the morning convection, the early day showers and clouds that are currently in the region, clears out fast enough before the afternoon heating begins, and if surface temperatures manage to warm into the upper 60s to the low 70s by afternoon, the conditions become extremely favourable for tornado development. The thermometer climbing, the cap breaking, the instability being released. The peak tornado threat window is between approximately 3 p.m. and 9 p.m. Central Daylight Time. The highest risk corridor runs from Davenport, Iowa through western Illinois and into extreme southern Wisconsin, a corridor that includes cities like Cedar Rapids, the Quad Cities, and portions of the Chicago metro area. This is densely populated territory where tornado impacts would be severe. This is where people work and live and where hundreds of thousands go about their daily activities unaware of what may be approaching. And here is the critical question that determines what kind of tornado threat we are dealing with, the uncertainty that is driving much of the forecast discussion among meteorologists. Will the storms stay discrete, or will they merge into a line? Will they remain as individual supercells, or will they quickly upscale into a quasi-linear convective system? This is not an academic question. The answer changes the threat profile completely. If individual supercells manage to stay isolated, if they remain as separate storms rather than linking together, each one becomes a potential long-track tornadic storm. A discrete supercell in that corridor, with the kind of wind shear and instability that is available today, could produce a significant tornado and stay on the ground for miles, potentially 10 or 20 miles or more, cutting a damage path that takes hours to traverse. That is the nightmare scenario. That is what keeps experienced storm forecasters up at night, and it is entirely within the forecast envelope. That is part of what the models are considering. But even if the storms merge early, even if they link up into a squall line before producing classic supercell tornadoes, the threat does not go away. It does not diminish. It transforms. It changes form, but not substance. QLCS tornadoes, embedded within the leading edge of the line, remain possible as the system pushes east through Chicago and into Indiana and Michigan overnight. The tornado type changes, the mechanism changes, the duration changes, but the danger does not disappear. The tornado threat simply becomes a different kind of threat, one that's harder to see, harder to warn for, and potentially harder to survive because of the nighttime timing. Damaging winds of 60 to 80 miles per hour are expected to be widespread within the enhanced risk area, regardless of which storm mode dominates. Those winds can blow roofs off houses, push over trees, turn loose objects into projectiles. Hail up to ping-pong ball size is forecast, concentrated along the Mississippi River Valley. Ping-pong ball hail does not sound catastrophic until you realize that something is moving at terminal velocity when it comes down. Impacts matter. A hailstone that size coming down at 60 miles per hour can shatter windshields on impact. It can destroy a crop field. It can injure a person caught in the open. And then comes the critical overnight phase. After the supercell window closes at sunset, the storms are expected to consolidate into a quasi-linear convective system, a long line of thunderstorms pushing east through the Chicago metro and beyond, QLCS tornadoes. in the middle of the night, embedded in rain, wrapped in precipitation so heavy that visibility becomes almost zero. This is the phase when people are in bed, when warning lead times are shortest because visual confirmation is impossible, when the only way people know a tornado is passing nearby is sound, the roar of wind, the sound of debris hitting houses, the breaking of glass, the crashing of trees. This is when tornadoes kill the most people relative to their intensity. But here is something important to keep in perspective. Today is not even the main event. The Storm Prediction Center is already looking ahead to Friday, with a level of concern in their language that suggests this may be the most significant day of the entire outbreak. The models are still converging on that forecast. The confidence is building. Friday may be worse than today. Before we get there, though, you need to understand the two completely different machines that make tornadoes, because both of them are running this week, and they are running in sequence. One follows the other. Supercells in the afternoon, QLCS at night. Then the cycle repeats Friday and Friday night. Part 3. What is still coming? April 4th and 5th. The SPC day? 2 outlook for Friday, April 4th, carries an enhanced risk from northern Missouri through southern Iowa. A slight risk extends across the Ozarks, Oklahoma, and into northwest Texas. This is a broad area under significant threat, and this is where the language from seasoned meteorologists starts to become pointed and careful. Pay attention to the words they choose. This may be the most significant day of the entire outbreak. Not might be. Maybe. That is forecaster language for confidence, for conviction, for belief in the forecast. That is them saying they are still watching, still calculating as the models update. But the trajectory of the forecast is pointing toward Friday being worse than Thursday. Friday more severe than Thursday. The models are trending in the direction of higher impacts. The forecast is moving in the direction of greater danger. A surface cyclone, a low-pressure system that will be intensifying as it moves, will progress from northeast Kansas to southern Iowa by Friday evening, then continue northeastward into southern Wisconsin by early Saturday morning. This low is following a track that has historically produced violent tornado outbreaks when the atmospheric conditions are right. The path is proven, the location is known. Boundary layer dew points are forecast to rise into the 60s, along and south of the warm frontal boundary, the zone of moisture that will fuel the storm development. That is the fuel tank. And the instability measurement, the CAPE values, the convective available potential energy that measures how much potential energy the atmosphere has available to convert into updrafts, are forecast to reach 1,500 to 2,000 joules per kilogram across the warm sector. For reference, 1,000 joules per kilogram is enough for strong thunderstorms. 1,500 is strong. 2,000 is explosive. The atmosphere on Friday will be exceptionally unstable, primed for violent convection. And the hail threat on April 4th is something that deserves its own paragraph because it is genuinely threatening. It is part of what makes Friday potentially worse than Thursday. Initial supercells developing in Kansas and Nebraska by early afternoon could produce baseball-sized hail. That is 2.75 inches in diameter. Do not minimize that number because the size is important. The larger the hailstone, the faster it is falling when it reaches the ground and the more damage it does. Ping-pong ball hail falls at one speed. Baseball hail falls at a different speed, with more force, with more impact. That is not hail that dents your car and you drive away annoyed. That is hail that destroys your windshield on impact, creating a shower of glass inside your vehicle, shards of glass everywhere. It punches through skylights and greenhouses, the glass structures that are not designed to withstand that impact. It damages crop fields so severely that a season's work becomes total loss. A farmer's entire annual income can be wiped out in minutes. It can injure or kill a person caught in the open. Standing outside when baseball hail falls is dangerous. It can cause head injuries. It can cause serious trauma. This hail threat extends from Des Moines through Kansas City, Wichita Falls, and into Texas. A broad corridor, it affects not just rural areas but cities. The Des Moines Metro, the Kansas City Metro, both densely populated regions with hundreds of thousands of people. That is the scale of this threat. The tornado potential is most elevated in central and southern Iowa into northern Missouri, Kansas City, and western Illinois, right along the warm frontal boundary where the surface low-pressure system passes overhead. The vertical shear will be sufficient for supercells in the warm sector east and southeast of the cyclone track. This is a setup that veteran meteorologists recognize because it has produced significant tornadoes historically. When this specific configuration appears on weather maps, people pay attention. When you stack high CAPE, high SRH, and a discrete supercell in that zone, you can get a long-track strong tornado. Those are the combinations that are being discussed in the forecast offices and on weather desks right now. By Friday evening, the atmospheric pattern repeats what we are about to see tonight. The individual supercells, having done their damage, having spun up their tornadoes or failed to in some cases, begin to upscale into clusters. Those clusters merge into a quasi-linear convective system, a line of thunderstorms producing scattered to numerous damaging winds of 60 to 80 miles per hour, widespread across the entire line. Tornadoes embedded in the line remain possible as the QLCS develops that characteristic structure with embedded mesovortices. The line pushes east into Illinois overnight and towards St. Louis and Little Rock, carrying the severe weather threat along with it as it progresses through the night and into Saturday morning. Saturday extends the severe threat all the way to the Gulf Coast. A damaging wind threat is expected from Dallas-Fort Worth through Louisiana, Mississippi, and into Alabama by Saturday afternoon. A couple of tornadoes are possible if discrete supercells form ahead of the main line as the system interacts with the Gulf moisture. And at the same time, a completely separate phenomenon is developing on the other side of the cold front. Record high temperatures are forecast from the Ohio Valley to the mid-Atlantic ahead of the cold front, warm air being drawn northward by the circulation around the low. The same system producing blizzards in the Dakotas will push temperatures into record or near record territory across the eastern seaboard. That is the temperature gradient. That is what this system does. By Sunday, the active pattern is expected to quiet down, briefly. The atmosphere will catch its breath for a day, but it is forecast to return by mid to late next week. This is not a one-day event. This is a 5-day assault on the central and eastern United States, and the primary threat window is between now and Saturday evening, 4 days. Tornadoes, hail the size of baseballs, blizzards in the Dakotas, ice storms in the Great Lakes, wildfires in Colorado, flash floods from New York to Louisiana, and record heat building ahead of the cold front, all from the same system, all at the same time. But to understand why this week is different from an ordinary spring storm sequence, why this week is producing all of these extremes simultaneously, you need to know how a tornado actually forms. Not the simplified version you probably learned in school, the real one, the actual mechanics. And once you see those mechanics, once you understand the 3 ingredients and how they interact, you will understand why this particular setup has every forecaster in the country watching the same patch of sky. Part 4, the 3 ingredients. Every tornado on Earth, every single one that has ever touched down and caused damage, requires 3 atmospheric ingredients working together at the same time in the same place in space and time: instability, wind shear, and a trigger mechanism. These are not theoretical concepts. These are not academic categories. These are the exact 3 factors meteorologists are measuring right now, in real time, across the central United States as this outbreak unfolds. Understanding them is not some optional deep knowledge. It is the difference between watching this outbreak with confusion and understanding it with comprehension. It is the difference between knowing something is dangerous and knowing why it is dangerous. The first ingredient is instability, and the metaphor for understanding it is simple and visceral. Warm, moist air near the surface sits trapped beneath cooler, drier air aloft. The warm air at ground level wants to rise. It has the buoyancy to rise. The physics demand it. The density difference requires it. But it cannot because the cooler air above it acts like a lid, like a ceiling that the warm air cannot break through on its own. The cap, we call it. This invisible barrier sitting between the ground and the clouds. Now imagine a cork held underwater by force, pressed down by someone's hand. The moment you release it, the moment you remove that force, the cork does not drift gently to the surface at a leisurely pace. It rockets upward with force, accelerating as it goes, picking up speed as it climbs. That is what happens when something forces the warm surface air upward through the cool layer above. It rises explosively, accelerating as it goes, feeding on its own buoyancy, warmer than everything around it and continuing to accelerate upward until it runs out of energy or until the surrounding air temperature catches up. The updraft of a supercell is not a gentle current. It is a vertical wind tunnel with speeds exceeding 100 miles per hour, and vertical river of rising air. Meteorologists measure this potential energy with something called CAPE, which stands for convective available potential energy, expressed in units of joules per kilogram. A CAPE value of 1000 joules per kilogram is enough to produce strong thunderstorms, the kind that might produce damaging winds or large hail, the kind you do not want to drive through. Values of 2000 or more can power updrafts exceeding 100 miles per hour, updrafts so powerful they can suspend grapefruit-sized hailstones in midair without them falling, holding them aloft in a circulation until they grow so large that even the updraft can no longer hold them and they fall back down at terminal velocity. Think about that. A hailstone the size of a grapefruit travelling at something like 80 or 90 miles per hour when it hits the ground. That is what these updrafts are capable of suspending. This outbreak is producing CAPE values of 1500 to 2000 joules per kilogram across the warm sector. To put that in perspective, that is solidly in the severe thunderstorm range, the range where significant weather is forecast, the range where damage is expected and prepared for by meteorologists, and that CAPE is backed up by boundary layer dew points in the 60s Fahrenheit, which means the air near the surface is carrying an enormous amount of moisture. The air is saturated with water vapour. The air is holding as much water as it possibly can at those temperatures. That is a loaded atmosphere. That is an atmosphere where instability is high and available. That is an atmosphere where the cork is ready to be released. The second ingredient is wind shear, and this is where tornadoes separate themselves from ordinary thunderstorms. Wind shear is not a complicated concept. It is simply the change in wind speed or direction as you go up in altitude. Near the surface, winds might blow from the south at 15 miles per hour, a gentle breeze, barely moving the leaves on the trees. A few thousand feet up, higher in the atmosphere, they shift to the southwest at 40 miles per hour, a much stronger wind that would definitely be noticed if you were up there. Higher still, even higher in the atmosphere where commercial airplanes cruise, the jet stream screams from the west at over 100 miles per hour, a high-speed river of air moving faster than any commercial aircraft can travel if going against it. That difference in speed and direction across altitude, that variation, creates something you cannot see but can absolutely measure and quantify. It creates a rotating horizontal tube of air, spinning like a log rolling in a river. The rotation is in the horizontal plane initially, parallel to the ground, invisible, unnoticed, but present, but real, but ready. But when a thunderstorm's powerful updraft comes along, when that rising air mass encounters this rotating tube, the updraft tilts the axis of rotation from horizontal to vertical. The log that was rolling along the ground starts rolling upward. The horizontal spin becomes vertical spin. That is the beginning of a tornado. That is the moment when a strong thunderstorm becomes a tornadic supercell. Meteorologists track this rotational energy available in the atmosphere with a measurement called storm relative helicity, abbreviated SRH. SRH measures the rotational energy available to a storm. When SRH is high, there is a lot of this rotational energy available, plenty of rotation already built into the wind profile. When it is low, there is not much. The air is primed to spin when SRH is high. When it is low, even a strong updraft might produce a non-tornadic supercell, a storm that is severe but not spinning. The difference in SRH values can make the difference between a dangerous hailstorm and a tornadic supercell. And right now, across the enhanced risk area, SRH values are extremely high, meaning the air is loaded with potential rotation. It wants to spin. The wind shear is there. The horizontal rotation is already being created by the wind change with altitude. All it needs is the right trigger and the right updraft to make it happen. The cork is in position. The cap is holding. The shear is there. All the system needs is the release mechanism. The third ingredient is the trigger mechanism, and this is the specific event that releases the instability and sets storms in motion. In this outbreak, there are 3 possible triggers at work simultaneously. The cold front is one trigger. A frontal boundary where cold air mass meets warm air mass always provides forcing that can lift the warm air and release the instability. The dry line is another, where hot, dry air from the west meets warm, moist air from the south. The density contrast along that boundary forces aggressive lifting, and the warm frontal boundary associated with the surface low pressure system is a third trigger. Any of these 3 boundaries could set off convection, could be the mechanism that forces the warm air upward and releases the instability. In fact, all three are expected to produce storms. The dry line in the early afternoon producing the first round of supercells, the cold front and warm front in the later afternoon and evening, producing the second round, the one with the highest tornado potential. Why all three of these ingredients are loaded right now is a question worth asking. Why is this outbreak different from a typical spring storm situation? Why is this day worse than normal spring days? The answer is that all four of the atmospheric components that feed these ingredients are in place simultaneously. All four, at the same time, in the same place. Gulf moisture is surging north with dew points in the 60s, providing the moisture fuel for the instability. The Gulf is sending its most energetic air northward. Dry air from the Rockies is pouring in from the west, creating both the cap that suppressed convection this morning and the dry line that is about to trigger the first storms. Two benefits from the same air mass. Polar air is crashing south behind the cold front, the contrast between that Arctic air mass and the warm air of the warm sector being extremely sharp. That temperature contrast is not gradual, it is dramatic. And the jet stream is driving everything. The negatively tilted trough providing extreme wind shear. The jet stream is in the right position. It is strong. It is positioned to provide maximum shear over the area where storms are expected to form. All four components are in place. All four are running hot. All four are at their maximum intensity. The cap, by the way, is worth explaining because it is the mechanism that has allowed instability to build all day. Air flowing over the Rockies from the west arrives at the plains hot and dry at altitude. This warm layer aloft is the cap, the lid that prevents convection during the morning. Instability builds all day like pressure in a closed container. The warm air at the surface wants to rise, but it cannot get through the cap. The tension builds, the pressure increases. When the cap finally breaks, usually by afternoon heating or the arrival of a frontal boundary, the storms that erupt are violent. The longer the cap holds, the more instability that can build. This cap held through the morning of April 3rd, allowing instability to accumulate. That is why the peak tornado window starts at 3 p.m. Central Daylight Time. That is when the cap is expected to break. This is not abstract atmospheric science. Every one of these ingredients is running hot right now across the central United States. This is not a forecast. This is what is happening. This is the state of the atmosphere right now at this moment. The question for this afternoon is not whether storms will form. Storms will form, something will trigger. The atmosphere is loaded, the instability is there, the convergence boundaries are there, storms will form. The question is whether the storms that form will rotate. The question is whether the wind shear will be captured by the updraft and tilted into a mesocyclone, that rotating column of air within the updraft. The question is whether that mesocyclone will tighten and descend to the ground. Will the rotation tighten enough that it reaches the surface? Will the vorticity become concentrated enough that a funnel cloud forms? Will that funnel cloud touch down? Those questions are still being answered. They will be answered in the next 6 hours. But the ingredients are in place. Everything that needs to be there is there. Part 5. 2 tornado machines. Not all tornadoes are made the same way, and this outbreak is designed to feature both major types of tornado production working in sequence. This is important because the 2 machines operate on completely different principles, produce different damage patterns, and create different kinds of warning situations. Understanding the difference is understanding why meteorologists talk about this outbreak in layered terms, why they separate the afternoon threat from the overnight threat. A supercell is a single, massive thunderstorm with a deep, persistent rotating updraft called a mesocyclone. The rotation is visible on radar as a hook echo, a curved appendage on the southwest side of the storm where rain and hail wrap around the rotating updraft in a way that looks like a fishing hook if you view it from above. The hook shape is the visual signature of rotation. It is the radar signature that tells meteorologists the storm is rotating. When the rotation tightens, and when it descends from the cloud base to the ground, when the mesocyclone tightens down to surface level, a tornado is born. Supercells are the most dangerous individual storms on Earth. Their tornadoes account for the vast majority of violent tornadoes, the EF4 and EF5 level storms that cause the most damage and the most fatalities. The structure of the supercell, the organization of its updraft and its downdraft, the way it manages its own dynamics, allows it to persist for an extended time, sometimes for hours. A supercell tornado can remain on the ground for an hour or more, travelling across the landscape and leaving destruction in its wake the entire time. A single tornado from a single supercell can cut a damage path tens of miles long, maybe even longer, tracking across counties and crossing state lines, and the damage path marks the movement of one continuous vortex that was in contact with the ground for that entire distance. One continuous tornado, one track, one storm. On April 3rd, any discrete supercell that develops in southeastern Iowa or western Illinois has the potential to produce a long-track significant tornado, a tornado that could rival the intensity of the Union City, Michigan tornado that we covered on video 15. Union City was EF3, 8 fatalities. This is the primary tornado threat meteorologists are most concerned about for this afternoon. This is the threat that makes forecasters write strong language in their text discussions. This is the threat that justifies the enhanced risk. But there is a completely different engine that also makes tornadoes, and it works in a fundamentally different way. A quasi-linear convective system, abbreviated QLCS, is not one rotating storm. It is not a supercell. A QLCS is a long line of thunderstorms moving as a unified front, acting as a single coherent system instead of individual cells competing with each other. The shelf cloud you see when a squall line moves through, that dramatic wall of clouds that appears to be moving toward you, is the visual manifestation of a QLCS. It is the boundary between the cool outflow from the storm and the warm air ahead of it. It is the surface gust front rendered visible, and it can be impressive and intimidating and hundreds of miles long, a continuous wall of clouds stretching from one horizon to the other. QLCS tornadoes form differently than supercell tornadoes. Instead of rotating updrafts as the primary mechanism, instead of a persistent mesocyclone, small mesovortices spin up along the leading edge of the gust front. These are smaller, more localized rotations that develop from the wind shear along the gust front boundary. They typically occur where the line buckles or bows outward, where the gust front has a local maximum in its strength. The structure of the line itself creates the rotation opportunity. These tornadoes tend to be weaker than supercell tornadoes, typically EF0 to EF2, as opposed to the EF3, and above that supercells can produce. They are also shorter lived. A QLCS tornado might be on the ground for 1 mile or 2 miles, a relatively brief contact with the surface. Whereas a supercell tornado might be on the ground for 10 or 20 miles, a track that spans counties. But do not confuse shorter duration with less dangerous. Shorter does not mean less lethal. QLCS tornadoes are extremely dangerous for 2 critical reasons. First, they are often embedded in heavy rain, nearly invisible even to nearby observers. Rain-wrapped tornadoes with no visible funnel cone, just a wall of rain with tornado force winds embedded in it. A person could be standing a quarter mile away and see nothing but rain. The visibility could be near zero. You could be looking out your window and seeing nothing but rain and not realizing that a tornado is moving toward you within that rain. The only indication they might have that a tornado is passing nearby is sound, the one sensory input that penetrates the rain curtain. The roar of wind that sounds different from normal heavy rain wind. The debris striking structures, the distinctive sound of impact. The breaking of glass and the crashing of trees. By then it is too late. By then you are already in the damage path. By then the tornado is upon you. The warning may have been issued. You may have received the alert on your phone. But if you did not see the tornado coming, if the rain prevented you from seeing it, you may not have had time to react even if you knew it was coming. Rain-wrapped tornadoes are the invisible killers of the tornado world. Second, they frequently occur at night, after the supercell phase ends and the storms merge into a line. People are asleep. Warning lead times are shortest because visual confirmation is impossible. The first time many people know that a tornado is passing nearby is when they feel the house move or hear the sound of destruction beginning. By the time they wake up, by the time they process what is happening, the tornado may already be moving away. The overnight phase of this outbreak, as the line pushes through Chicago and into Michigan and Indiana after sunset, is when QLCS tornadoes are most likely. This is when the fatality risk is elevated. This is when people are most vulnerable. This outbreak is designed by the atmospheric pattern to feature both machines in sequence. Discrete supercells during the afternoon peak, the 3 to 9 p.m. Central Daylight Time window, when instability is highest, and the cap has broken. Then the storms merge into a QLCS overnight. The tornado threat does not end when the supercells end. It does not disappear. It transforms into something harder to see and harder to survive. Then, Friday afternoon, the pattern repeats. Another round of supercells, then another QLCS as storms consolidate late Friday and Friday night. 2 complete cycles in 2 days. 2 separate windows of tornado production, each with different characteristics, each requiring different warnings and different responses. The April 2nd example shows exactly how this transition works in practice. The Kalona, Iowa supercell produced that tornado with the debris ball clearly visible on radar. The storm was discrete, individual, rotating violently. Then the storm evolved into a mesoscale convective system as it moved east. The supercell became part of a larger structure, its individual rotation becoming one feature within a larger organization. The system continued to organize and produce impacts. The Cleveland mesovortex was a direct result of this transition. It was not a classic supercell tornado. It was a small mesovortex embedded in the leading edge of a QLCS, tornado-strength winds from a feature that technically was not a tornado by the traditional definition. But the damage was real. The power outages were real. The NWS still issued a tornado warning for it, because the wind speeds warranted warning regardless of the specific mechanism. This pattern, this two-machine operation, is what gives meteorologists pause about this outbreak. It is not just the afternoon supercells, it is the nighttime QLCS that comes after. It is the vulnerability that comes when people are asleep and the tornado is invisible. It is the transition that does not stop the threat but transforms it into something harder to prepare for. Understanding this distinction is understanding why the warnings will be different throughout the event, why the messaging changes as the pattern evolves. Part 6. The EF scale. What the numbers actually mean. Tornadoes are rated on the enhanced Fujita scale, running from EF0 to EF5. The scale is based not on measured wind speeds but on damage indicators, the visible destruction left in the tornado's wake. This distinction exists because direct wind measurements inside an actual tornado are nearly impossible to obtain. How do you place an instrument in a tornado to measure the wind? You cannot. You observe the damage and work backward from the damage to estimate the wind speed. The scale reveals something important about tornadoes. Even a weak tornado is life-threatening. Even an EF0 can kill you. An EF0 tornado has winds between 65 and 85 miles per hour. 65 to 85. At this intensity, the tornado breaks branches off trees, damages signs, tears shingles off roofs. The damage is noticeable and the costs add up, but a permanent structure provides adequate shelter. You're survivable in any permanent structure if you are away from windows. 65 to 85 miles per hour happens to be roughly equivalent to the straight-line winds that were recorded in Cleveland on April 2nd, 75 miles per hour at Cleveland Edgewater. Those straight-line winds caused widespread tree damage and power line damage across Ohio. That was EF0 equivalent. An EF0 is not trivial. An EF1 tornado has winds between 86 and 110 miles per hour. At this intensity, the tornado strips roofs from houses, overturns mobile homes, pushes cars off roads. The structural damage is obvious. Windows break. Structural failure begins. An EF1 is dangerous, but with shelter, you can survive it. If you are in an interior room of a permanent structure, below ground or without windows, an EF1 is unlikely to kill you if the structure does not completely fail. An EF2 tornado has winds between 111 and 135 miles per hour. This is where things become serious. The tornado tears roofs completely off well-built homes. It destroys mobile homes entirely, turning them into debris. It snaps large trees, not just branches but the whole tree from the ground. Debris from destroyed structures becomes projectiles moving at tremendous speeds. This is where permanent homes start to suffer major structural failure. An EF2 can kill people in well-built houses if they are not in an interior room or below-ground shelter. An EF2 is where the survival equation changes. An EF3 tornado has winds between 136 and 165 miles per hour. At this intensity, the tornado destroys entire stories of well-built homes. It overturns trains. It debarks trees, stripping the bark from the wood. Heavy cars are thrown. The March 2026 tornado in Union City, Michigan, which we covered on video 15, was rated EF3. That tornado killed 8 people. This is the category that separates survivable damage from catastrophic destruction. An EF3 does not show mercy to well-built structures. An EF4 tornado has winds between 166 and 200 miles per hour. Winds at this intensity level well-built homes completely, sweep them from their foundations, turn them into rubble scattered across the landscape. Vehicles become airborne missiles, can be thrown hundreds of yards from their starting position. Trees are snapped and debarked. Survival outside of a below-ground shelter or a reinforced safe room becomes uncertain. An EF4 changes the discussion from damage to survival probability. An EF5 tornado has winds exceeding 200 miles per hour. 200. More than that, potentially much more. At this intensity, the damage is total. Well-built frame homes are swept clean off their foundations. Steel-reinforced concrete structures are critically damaged. Automobiles become airborne projectiles. The ground itself is scoured by the tornado, the soil removed from the surface. EF5 tornadoes are rare. Only 59 have been recorded in the United States since 1950. Only 59 in 75 years of recorded tornado history. But when they occur, they represent the most violent phenomenon in Earth's atmosphere. More destructive than hurricanes, more intense than any other weather event. For this outbreak, the SPC hatched tornado probabilities, the shaded regions on the Day 2 outlook, indicate the potential for EF2 and stronger tornadoes. EF2 and stronger means tornadoes strong enough to destroy homes and kill occupants even with shelter. The corridor from Davenport through western Illinois is where this risk is highest. When the SPC hatches probabilities for 2 and stronger, when they put their confidence behind a specific region, people in that region need to take this seriously. This is not a marginal threat. This is a forecast for significant tornadoes with the potential to cause fatalities. The scale itself, in its numerical progression, tells a story about how tornado danger escalates. Below EF2, you have a reasonable chance of survival with proper shelter. At EF2 and above, that certainty vanishes. The tornado becomes capable of destroying well-built structures. The safety margin shrinks. The danger is real. Part 7. The Invisible Killers. The single most dangerous characteristic of a tornado is not its wind speed. It is not whether it reaches EF3 or EF4 intensity. It is whether you can see it coming. A visible tornado gives you time to react. A visible tornado can be reported by spotters. A visible tornado's approach can be predicted, and warnings can be issued with some lead time. An invisible tornado, a tornado you cannot see because it is the middle of the night or because it is buried in rain, that is a tornado that kills. That is a tornado that turns statistical disadvantage into mortality. The statistic is sobering, and it is measurable. Tornadoes that occur after dark are 2.5 times more likely to be fatal than daytime tornadoes. 2.5 times. That is not a marginal difference. That is a fundamental shift in danger. The reason is brutally simple and goes back to basics. People cannot see tornadoes at night. They cannot see them. During daylight, storm chasers and trained spotters and ordinary citizens out of doors can see a tornado and report it. Visual confirmation often beats radar confirmation in terms of lead time. A spotter sees a funnel on the ground and immediately calls it in. The warning is issued based in part on that visual confirmation. A person hears the siren or gets the alert and has a few minutes to seek shelter before the tornado arrives. It is not much, but it matters. It matters for survival. At night, that entire early warning system vanishes. The tornado is invisible. People are asleep. The only way of detecting it is radar, and radar confirmation takes time. You have to see the rotation. You have to issue the warning. The warning has to propagate through the system and reach people through their phones or their weather radios. Then they have to wake up. Then they have to process what they are hearing. Then they have to get to shelter. That lag time, that accumulated delay, means the tornado arrives before warning-led times that would be adequate in daytime become dangerously short at night. Minutes become seconds. Warning becomes advisory. Advisory becomes aftermath. Rain-wrapped tornadoes compound the visibility problem and can occur at any time, day or night. When a tornado is embedded in a curtain of heavy rain, it is invisible even to observers standing nearby. Not 2 miles away. Nearby. A quarter mile away. The rain is too heavy. The visibility is too poor. A person could be standing in the open and unable to see a tornado that is a couple hundred yards away if there is heavy rain in between. The only indication of the tornado's presence is sound, the roar of wind that sounds different from ordinary heavy rain wind, the sound of debris striking structures, the breaking of glass, the crashing of trees. By the time you hear it, by the time you process that sound and understand what it means, the tornado may already be passing over you. That delay can be fatal. Meteorologists have a tool for seeing what people cannot see. It is called dual polarization radar, and it includes a product called the correlation coefficient. Correlation coefficient measures how similar the shapes of objects in a radar volume are to each other. Raindrops are roughly the same shape, all roughly spherical or slightly oblong. In rain, correlation coefficient values are very high, 0.95 to 1.0. But when a tornado lofts debris into the air, pieces of wood and metal and insulation and dirt, all of those objects have highly variable shapes. They are not uniform, they are chaotic. When that diversity of shapes enters the radar beam, the correlation coefficient value drops dramatically, often below 0.80. When a meteorologist sees a low correlation coefficient value co-located with a strong rotational couplet on the velocity product, the interpretation is certain. There is a tornado doing damage on the ground. The debris ball, as it is called, is confirmation that the tornado is real and significant. The Kalona, Iowa tornado on April 2nd showed a clear debris ball on the correlation coefficient product. The evidence of damage was there on radar. The tornado was confirmed to be on the ground, lofting objects into the air. The radar signatures were unmistakable. This is what NWS forecasters are watching for right now as this outbreak develops. They are looking for debris balls. When they see one, when they observe that low correlation coefficient value co-located with rotation, the situation changes. The warnings change, the confidence increases, the messaging becomes more urgent. What was a possible tornado becomes a confirmed tornado. What was a warning based on radar signatures becomes confirmation that actual damage is occurring on the ground. That confirmation is critical because it allows forecasters to issue warnings with greater certainty, which allows people to make faster decisions about seeking shelter. The debris ball is proof. The debris ball is confirmation that the tornado is real and that it is doing damage. This outbreak has the potential for both of these hazards, nighttime tornadoes and rain-wrapped tornadoes, working together in the worst possible way. The QLCS phase that pushes through Chicago, Indiana and Michigan overnight April 3rd into April 4th is a classic setup for nighttime rain-wrapped QLCS tornadoes. The storms will be organized, moving fast, producing rain heavy enough to hide the tornadoes within them. The timing will be wrong for visibility. People will be asleep. Friday evening and Friday night also threaten after dark tornadoes, as storms upscale into a squall line and push east after sunset. 2 consecutive nights of elevated nighttime tornado risk within the same event. If you are in the path of this outbreak, if you live in the enhanced risk area or the slight risk area, you need to know right now how you are going to receive warnings that will wake you up. Not your phone on silent sitting across the room, not a text message that you might sleep through, not notifications turned off, a weather radio with an audible alarm, a dedicated alert system that wakes you up when a warning is issued. Your phone should be configured so that tornado warnings come through as audible alerts even if the rest of your notifications are silenced. Your bedroom should have a way to receive those alerts. Know your safe room right now. Not during the storm, not when the tornado's approaching. Right now, identify it, know where it is. Interior room, lowest floor, away from windows. Interior means no external walls. Lowest floor means ground level or below ground if possible. Away from windows means fully protected from potential projectiles. A bathroom in the interior of the house, a basement closet away from the exterior walls, a hallway in the interior. A room like that identified now will be a room you can get to in the dark without confusion. If you are in a mobile home, do not shelter in place during a tornado warning. Mobile homes are not safe in tornadic winds. Identify a permanent structure you can reach immediately when a warning is issued. A neighbor's house, a community shelter, a building designed to withstand tornado-force winds. Do not wait for the warning to locate that structure. Know where it is now. Put it in your phone, write it down, know the route. If you have neighbors in mobile homes, know where they can go. Help them identify shelter. These preparations take minutes and they save lives. The minutes you spend right now reading this and making a plan are the minutes that could save your life tonight. The danger profile for this outbreak is not just about whether tornadoes form. It is about whether they form when you can see them or when you cannot see them. It is about the visibility situation. It is about whether darkness and rain will obscure the threat. And the forecast says both. Afternoon supercells in the light, supercells with visible rotation that chasers and spotters might see, daytime tornadoes that people can watch approach, overnight QLCS in the rain and in the dark, mesovortices embedded in precipitation cores, nighttime tornadoes that are invisible, rain-wrapped tornadoes that are impossible to see, both types of tornado production, both vulnerability windows, both risks. This is the full spectrum of tornado danger in a single event. This is why the outbreak is so dangerous. Part 8. Why here? No place on Earth produces more tornadoes than the central United States. That is not hyperbole, that is measured fact. The Great Plains and the Mississippi Valley are the global epicenter of tornado activity. The reason is pure geography. 3 air masses collide in the central United States in a way they do nowhere else on the planet. They do not collide the same way in Argentina or Australia or any other location that has experienced notable tornado activity. There is something unique about this geography, something about the latitude and the proximity of mountains and the jet stream that makes this region special in ways that favor tornado production. From the south comes the Gulf of Mexico, pumping warm, moisture-laden air northward. This air is unstable, energy-rich, loaded with water vapor. From the west comes hot, dry air off the elevated terrain of the Rocky Mountains and the high deserts beyond them. From the northwest comes cold, dry air plunging south from the Arctic and the Canadian interior. When these 3 air masses converge, when they come together in the same region, the temperature and moisture contrasts create explosive instability. The contrast is not gradual, it is sharp. Air mass boundaries are hard lines, transitions that span miles or sometimes just hundreds of yards, from warm to cold, from moist to dry, from light to dense. When those contrasts are that sharp, the atmosphere becomes volatile. The Rocky Mountains themselves play a critical role in making the central United States the tornado capital of Earth. Air flowing over the Rockies from the west arrives at the plains fundamentally transformed. The mountains force the air to rise. As air rises, it expands and it cools. Cool air cannot hold as much moisture as warm air, so that moisture is removed from the air column by precipitation on the western slopes of the Rockies. Snow and rain fall on the mountains. That moisture that was in the air gets taken out. By the time the air crests the mountains and begins to descend on the eastern side, having lost its moisture to precipitation, it is hot and it is dry, parched, dehydrated. Air that sinks from altitude warms adiabatically, warming further as it descends toward the surface through compression. The air warms further and further. The result is hot, dry air aloft over the Great Plains, a warm cap that suppresses convection during the morning and early afternoon. This cap is essential to the tornado breeding mechanism. It is the mechanism that allows instability to accumulate. Instability builds all day like pressure in a container. The warm, moist air at the surface wants to rise but cannot get through the cap that is sitting above it. The lid holds, the pressure builds. When the cap finally breaks, usually in the mid-afternoon by surface heating from the sun or by the arrival of a frontal boundary that forces air upward, the convection that erupts is explosive. The amount of energy that has accumulated is released all at once. The longer the cap holds throughout the day, the more instability that can accumulate. A cap that holds until 4 p.m. allows more instability to build than a cap that breaks at 2 p.m. The timing matters, the duration matters, the jet stream adds the final critical ingredient: wind shear. In spring, the jet stream is at its strongest and most volatile over the central United States. The steering flow is fastest, the temperature gradients are steepest. The jet stream is positioned across North America where it can interact with warm, moist air from the Gulf and cold air from Canada. The jet stream provides the extreme speed and directional shear that supercells need to rotate and produce long-track tornadoes. The jet stream is the engine that makes everything work. Without the jet stream providing sufficient wind shear, the supercells would not rotate even with high instability. The supercells would be strong, but not tornadic. The jet stream is what converts strength into rotation. This is why April, May and June are the peak months for tornado activity in North America. The jet stream is still strong during those months. The jet stream is still positioned to interact with moisture from the south. This is why the corridor from Texas to Iowa is called Tornado Alley. It is called that because the geography produces it. The geography and the jet stream location and the moisture availability all come together. This particular outbreak illustrates the mechanism perfectly. It is a textbook case. Gulf moisture is surging north with dew points in the 60s, providing the moisture fuel for instability. Dry air is pouring in from the west after crossing the Rockies, creating the cap and the dry line that will trigger the first round of storms. Polar air is crashing south behind the cold front, the contrast between that Arctic air mass and the warm air of the warm sector being extremely sharp and creating the trigger for the second round of storms, and the jet stream is driving everything, the negatively tilted trough providing extreme wind shear. All four components are in place simultaneously. The geography is set. The collision is happening right now. Understanding this geography explains why the corridor from Davenport through western Illinois is the hotspot right now. It is not random chance that this is where the highest tornado risk is forecast. It is not arbitrary. It is where the three air masses are colliding with maximum contrast. It is where the dry line will form and trigger the initial supercells. It is where the cold front will arrive with maximum intensity. It is where the atmospheric conditions are right for tornado production. The forecast hotspot is there because the geography demands it. Part 9. The same system producing everything. While tornadoes threaten the warm sector of this system, while the instability is building and the supercells are being triggered and the updrafts are rising over Iowa and Illinois, something completely different is happening in the cold sector. 33 winter storm warnings are active across Montana, Wyoming, the Dakotas, and northern Minnesota. 33 separate warnings for separate regions, each one indicating dangerous winter weather. That is a massive number of winter warnings for early April, 33. That number reflects how significant and how widespread the winter weather threat is. 6 to 12 inches of snow is forecast from the Dakotas through northern Minnesota, with wind gusts of 35 miles per hour creating blowing and drifting snow and making travel very difficult to impossible. Travel will be hazardous. Visibility will be reduced. Roads will become impassable. In the Montana mountains, in the Absaroka Range and the Beartooth Range and the Bighorn Mountains, 1 to 2 feet of snow is expected with wind gusts reaching 50 miles per hour. 50 mile per hour winds with a foot or two of snow, that is dangerous mountain weather. That is the kind of conditions that create search and rescue operations. Snow in early April in high elevation areas is not unusual. Mountain ranges get snow in April. Snow of this magnitude with this much wind is significant and dangerous. This is not just a light dusting. This is a major spring snowstorm. The Wisconsin juxtaposition brings this all into focus. Ice storm warnings in Green Bay with 0.25 to 0.5 inches of ice accretion forecast. The same state, the same day, is also under marginal to slight risk of severe thunderstorms including hail. The same state, Wisconsin. Going from ice storm conditions to hailstorms in one state in one day is not a normal forecast. This is what happens when the temperature gradient is extreme. This is what happens when you have a collision of air masses so sharp that you can go from winter to spring in an hour of driving time. That gradient is also what is driving the tornado threat. The same system that might produce a tornado in Iowa this afternoon is the same system that is producing ice storm conditions in Wisconsin at the exact same time. That is the scale of the spatial variation. That is the temperature contrast. But even the ice and the snow do not tell the complete story of what this system is doing, because there is also fire weather. 13 red flag warnings are active across Colorado's Front Range and eastern New Mexico. 13 separate warnings for critical fire conditions. The SPC Fire Weather Outlook shows critical risk. Critical. The conditions are extraordinary by any standard. Northwest winds of 20 to 35 miles per hour, with gusts reaching 45 miles per hour, and even 60 miles per hour near the foothills. 60 mile per hour winds. That is hurricane force wind gusts. That is enough to break tree branches. That is enough to spread embers rapidly. Relative humidity as low as 10% in southeastern Colorado and 13% elsewhere along the Interstate 25 corridor. 10% relative humidity is exceptionally dry. The air is parched. It is desiccated. Any moisture in vegetation or in the soil is being wicked away by the dry air. These are the conditions that fire departments fear most. These are the textbook conditions favourable for rapid fire spread. A fire that starts small from a lightning strike or from a discarded cigarette can become massive in hours. Existing fires can expand exponentially. In New Mexico, strong northwest winds and very low humidity stretch along the Interstate 40 corridor from Cleans Corners all the way to the Texas border. The dry air is in place, the winds are in place, the fuel is available from last year's vegetation and from areas burned in recent years that have regrown and become available to burn again. The connection here is direct and obvious once you understand the mechanism. The tornado threat, the blizzards, the ice storms, and the fire weather are not separate events from separate weather systems. They are different expressions of the same atmospheric pattern. They are different faces of the same monster. The extreme temperature gradients that drive the tornado formation, the contrast between hot and cold, between moist and dry, those same contrasts are producing ice in Wisconsin and snow in the Dakotas and fire conditions in Colorado. The fire weather conditions in Colorado are a direct consequence of the dry air mass that is pouring in from the west, the same dry air that creates the dry line where tornadoes are born. The same system that might produce a tornado in Iowa this afternoon is the same system creating conditions for a catastrophic wildfire in Colorado. Different location, different mechanism of destruction, same source, same atmospheric system, one atmosphere doing everything at once. Part 10. Is this the new normal? Video 21, released in mid-March, covered a compound event, a system producing simultaneous blizzards, tornadoes, heat waves, and fire conditions, all from one atmospheric system. That video hit 160,000 views. 160,000. The channel has plenty of videos, plenty of content, plenty of uploads. 100,000 views is not unusual for some topics, but that particular video resonated in a way that suggested something more than mere weather interest. People were not surprised by a storm. They were recognizing something. They were seeing a pattern. That was 3 weeks ago. 2 weeks after that video, another compound event occurred. The March 26th atmospheric anomaly. Then 2 weeks after that, this one. 3 compound events in 3 weeks. 3 separate occurrences of simultaneous multiple category extremes from single coherent atmospheric systems. 3 times in 3 weeks the atmosphere produced everything at once. The question people are starting to ask, the question that Video 21 raised so prominently, is whether this is what spring looks like now. Is this becoming normal? Is the transition between winter and summer no longer gradual but violent? The science suggests the answer is more complicated than a simple yes or no. There is no simple binary answer to the question of whether this is the new normal. Weather whiplash is a real phenomenon driven by Arctic amplification and the changing jet stream. When baseline temperatures increase, the atmosphere holds more moisture. The warmer the air, the more water vapour it can hold in the gaseous state. When a cold air mass collides with extra warm, extra moist air, when that contrast between air masses becomes extreme, the contrasts are sharper than they used to be. The temperature gradients are steeper. The frontal collisions are more violent. The updrafts are stronger because there is more buoyancy available. The shear might be stronger, or it might be weaker depending on the configuration and the pattern, depending on how the jet stream is oriented. The relationship is complex, not straightforward. But the compound events, the simultaneity of extremes, appears to be increasing. The tornado season itself shows evidence of change. Tornado activity is expanding geographically, starting earlier in the spring and extending later into the fall. The activity is shifting eastward and southward from traditional Tornado Alley toward the Mississippi Valley and the southeast. That shift puts more people at risk because population density is higher in the southeast and the mid-Atlantic than in the Great Plains. More people are living in areas that are now seeing more tornado activity. The risk has not just changed, it has changed for more people. The climate signal on tornadoes specifically is complicated, not straightforward. It does not follow a simple linear relationship. Warmer temperatures increase atmospheric moisture and instability, more fuel for storms, more updraft potential, more energy available. But they can also reduce wind shear in some configurations, less spin, less rotation potential, different patterns. The net effect on tornado intensity and frequency is less clear than for heat waves, which are directly driven by warming, or hurricanes, which have a clear thermodynamic connection to ocean temperature. The hurricane connection is obvious. Warmer water means more energy for hurricanes. The tornado connection is more subtle. The research is ongoing. Scientists are still working on understanding the precise relationship. What is clear is that compound events, multiple simultaneous extremes from one system, are becoming more common. The March 16th event, the March 26th event, now April 2nd through 5th, 3 in 3 weeks. That is the pattern. That is what has changed. The simultaneity, the multi-category nature, the single system production of every extreme category. The satellite loops show record heat building in the east, while blizzard conditions persist in the north. The temperature dipole is real and visible and measurable. While Iowa is producing tornadoes and Wisconsin is ice, the mid-Atlantic is approaching record high temperatures. The same system is creating both extremes. The machinery that builds tornadoes is the same machinery that builds everything else. Understand the mechanism that produces a tornado, and you understand the mechanism that produces a heat wave, and the mechanism that produces a blizzard, all from the same system on the same day. The bigger story, the story beneath the headline tornado outbreak, is that the atmosphere is producing these multi-category simultaneous extremes with increasing regularity. The machinery is not broken. It is doing exactly what physics predicts it would do with more energy in the system. The tornadoes forming tonight are not mysterious. They follow rules we understand. They follow the mechanics we have explained. The wind shear, the instability, the trigger mechanism, the supercell updraft, all of it is mechanical, all of it is understood. But the frequency and the simultaneity, the way these extremes are being stacked together, the way every category of weather is produced by the same system in the same few days, that is the piece we are still integrating into our understanding. That is the part that does not fit the pattern of recent decades. That is the part that requires acknowledging that something in the behavior of the atmosphere has changed. Part 11. The conspiracy question. Large events like this one, events that command attention and that produce multiple categories of extreme weather and that stretch across thousands of miles, tend to attract alternative explanations. Weather modification and geoengineering theories surface with regularity when events this significant make headlines. It is worth addressing these directly and respectfully, because the concerns that drive interest in these theories often reflect a real intuition about the changing atmosphere. The HAARP facility, the High-Frequency Active Auroral Research Program in Alaska, is frequently cited in conspiracy theories as a weather weapon capable of steering storms or intensifying them. The reality of HAARP is that it is an ionospheric research facility that heats a tiny patch of the ionosphere to study plasma physics. It is not a weather weapon. The energy output of HAARP is minute compared to the energy in weather systems. The energy contained in a single thunderstorm dwarfs HAARP's total power output by many orders of magnitude. A supercell updraft is accelerating air vertically at speeds of over 100 miles per hour. The energy in that updraft exceeds what HAARP could produce in days. HAARP cannot influence weather systems thousands of miles away. The physics do not work. The energy is not available. The mechanism is not plausible. Cloud seeding is a real technology, entirely different scale. Cloud seeding introduces silver iodide particles into existing clouds to encourage precipitation. It works on individual clouds at local scales. It changes the microphysics within a cloud, affects how water condenses, affects how the cloud precipitates. It cannot create weather systems. It cannot steer fronts. It cannot generate tornadoes. It cannot change the movement of a system or its intensity. The dynamics producing this outbreak, the continental scale atmospheric mechanics involving air masses spanning thousands of miles and temperature gradients extending across multiple states, are incomprehensibly larger than the scale at which cloud seeding operates. Think about the scale difference. Cloud seeding affects one cloud, maybe affecting rainfall by 10 or 20% within that cloud. This system spans from the Rocky Mountains to the Atlantic Ocean. It spans from the Great Lakes to the Gulf of Mexico. The spatial scale is hundreds of miles. The energy involved is unimaginable. Cloud seeding is a garden hose. This outbreak is the ocean. Trying to control this system with cloud seeding would be like trying to change the direction of a hurricane with a fire hose. A more nuanced question worth discussing is whether the severity of these events is being adequately communicated to the public. The NWS enhanced risk is level 3 out of 5. To many people, enhanced sounds moderate. It does not sound critical, but a level 3 risk contains the potential for significant tornadoes and baseball-sized hail. it contains the potential for fatalities. Some meteorologists have questioned whether the SPC's risk categories adequately convey the danger of a level 3 risk to the public. When a level 3 can kill you, when the threat includes EF3 and above tornadoes, is the scale doing its job? Is the word enhanced capturing what the risk actually is? That is a legitimate discussion in the meteorological community. Address the core truth respectfully. These conspiracy theories come from a real place. They come from a sense that the weather is becoming more extreme. They come from a feeling that the explanations offered by conventional meteorology seem insufficient to match the magnitude of what people are experiencing. The science actually agrees with the instinct. The weather is becoming more extreme. The storms are becoming more violent. The events are becoming more frequent and simultaneous. The mechanisms are well documented. The atmosphere has more energy in it than it used to, and the evidence of that increased energy is quite literally falling on our heads right now. Tornadoes, hail, floods. The evidence is in the impact reports and the damage surveys and the satellite loops. Regardless of what you believe is causing these extremes, the threat is real and the data is clear. Part 12. The next 72 hours. Let us consolidate the active timeline because it matters to understand the sequence and the intensity window and how it builds. April 3rd afternoon, supercell phase, the individual storms, tornado potential Chicago Quad Cities and surrounding regions, peak window 3 p.m. to 9 p.m., Central Daylight Time. This is the primary supercell window, April 3rd to April 4th overnight, QLCS phase. The line forms, nighttime tornadoes embedded in rain, people asleep, warning lead times short. The most dangerous phase, April 4th afternoon, escalation, the second day. Baseball hail threat Des Moines through Wichita Falls. Supercells Iowa, Missouri, Kansas. Enhanced risk from northern Missouri through southern Iowa. Friday is worse than Thursday. Friday's the main event. April 4th to April 5th overnight. Second QLCS phase. Storms push east through Illinois towards St. Louis and Little Rock. The line continues overnight again. Saturday. Gulf Coast severe threat. The system pushes south and east, damaging winds Dallas-Fort Worth through Louisiana, Mississippi, Alabama. Record high temperatures Ohio Valley to mid-Atlantic. The transition zone shows the extremes. Sunday. Pattern quiets briefly. The first break, the moment of quiet. While those headline events are unfolding, while the tornadoes are being produced and the hail is falling and the supercells are organizing, several other elements of this same system are creating their own impacts. Temperatures from the Ohio Valley to the mid-Atlantic will approach or set records on Saturday ahead of the cold front, warm air being drawn northward by the circulation around the low-pressure system. Meanwhile, the Dakotas are buried in blizzard conditions, record heat and blizzard conditions, from the same system, on the same day. That is the spatial scale of what this system is doing. The breadth of impacts from this outbreak extends across the entire country. Tornadoes in Iowa and Illinois confirmed on April 2nd. 4 feet of water on streets in Ithaca, New York, the highest level of flood warning the NWS issues. Flash floods in Louisiana with 5 to 7 inches of rain in a matter of hours. Blizzard conditions in the Dakotas, ice in Wisconsin, fire weather critical risk in Colorado. The geographic footprint is continental. The system stretches from the Rocky Mountains to the Atlantic Ocean, from the Great Lakes to the Gulf Coast. One system, all of it at once. Meanwhile, the sun is also active right now. A G2 geomagnetic storm was observed on April 2nd. A coronal mass ejection is expected to arrive, potentially triggering G3 conditions. For the northern tier states getting hammered by this severe weather outbreak, the same northern tier states bracing for blizzards and tornadoes and ice storms, there is an outside possibility of aurora visible, the northern lights visible from the ground over Minnesota and Michigan and Wisconsin and the Dakotas. The northern lights while the tornado warnings are active. The northern lights while the blizzard rages. It is the kind of juxtaposition that defines this particular moment. 4 astronauts are currently heading to the moon during this geomagnetic storm. The core question that emerges from this sequence, the question that Video 21 raised, and that this outbreak reinforces, is whether we are entering a world where spring is no longer a gradual transition, but a violent collision of seasons. The March 16th compound event, the March 26th atmospheric anomaly, now this April 2nd through 5th sequence. 3 compound events in 3 weeks. 3 times in 3 weeks, the atmosphere produced multiple simultaneous extremes. 3 times. The pattern is repeating. The data is accumulating. The evidence is mounting. The atmosphere is not broken. It is not malfunctioning. It is doing exactly what physics predicts it would do with more energy in the system. More heat, more moisture in the air, sharper gradients between air masses. The tornadoes forming tonight are not mysterious. They are not anomalies that violate the laws of physics. They follow rules we understand. They follow the mechanics we have explained. The wind shear, the instability, the trigger mechanism, the supercell updraft. All of it is mechanical. All of it is understood. All of it can be explained. But the frequency and the simultaneity, the way these extremes are being stacked together, the way every category of weather is produced by the same system in the same few days, that is the piece we are still integrating into our understanding. That is the piece that represents a potential shift in the character of seasonal transitions. Call back to video 21. When that video hit 160,000 views, when it became one of the most viewed videos from the Skylab, it was not because people were surprised by a storm. People see storms all the time. They see tornadoes reported, they see blizzards forecast. But that many people watching, that many people engaging, it was because they recognized something deeper. They saw the pattern. They understood that this was not normal. They understood that the simultaneity was remarkable. They understood that 5 different categories of extreme weather do not usually happen from the same system in the same week. This video is another piece of that same pattern, another data point in an accumulating body of evidence, another case study in the compound event mechanism. The atmosphere is not being weaponized. It is not being controlled by HAARP or cloud seeding or any external force. The atmosphere is not malfunctioning. It is responding to the changes in the energy balance of the planet. More energy in the system means more violent storms, more fuel available for convection, more moisture in the air, more potential energy available to convert into wind and updrafts. More contrast means more extreme weather. Sharp contrasts between air masses produce violence. The April 3rd to 5th sequence is brutal. The death toll, if the worst forecasts verify, could be significant. Multiple fatalities are possible. Multiple communities could be impacted, but the mechanisms are understood, the physics are known, the changes are measured and quantifiable. We can measure the wind shear, we can measure the instability, we can measure the moisture, we can measure the temperature contrasts. Everything that produces this outbreak can be quantified, and the next 72 hours are about to add more evidence to the pile, more data points, more impact reports, more observations. The pattern is expected to quiet by Sunday. The atmosphere will catch its breath, the winds will diminish, the instability will be released, but it is forecast to return by mid to late next week. Another system in the queue, another series of severe weather threats, another opportunity for compound events. The machine is not shutting down. This is the rhythm now. Oscillations of extreme weather, violent transitions between seasons. Thank you for sticking around with me tonight. Make sure to subscribe to the Skylab as we keep track of this developing story, and I'll see you in the next one.